Hello, everyone. I hope that each and every one of you is having a great day. This is Jeff Babbitt, and I am a solution architect at Fujitsu. In this presentation, I would like to do something a little bit different. Today's optical transport systems involve a lot of technical terminology. That is because the solutions contain a lot of physics, science, and engineering concepts. So today I would like you to help understand some of these terms and concepts. This is in no wise comprehensive, but more of a high-level understanding. So no math. Let's get started. Since the beginning of telecommunication systems, there has been a perpetual need for more traffic on the transmission system. It started with wires, which led to the nationwide wired infrastructure and all of these telephone poles and telephone cables that crisscross our country. This inexorable demand for more traffic led to the development of new technologies that allowed more calls and more data on the wire. It also led to other technologies being used in our telecom network, including coaxial cable, wireless, and fiber optic cables, as well as some others. This presentation will focus on the trends and technologies associated with fiber optic transport. In 1962, semiconductor lasers were first. Let's start this one differently. In order to have an optical transport system, you need to have a laser. More specifically, a semiconductor-based laser. In 1962, semiconductor lasers were first developed, but they weren't really commercially useful since they required a tank of liquid nitrogen to keep them cool so that the lasing action could occur. Subsequently, in 1975, the first commercial room temperature semiconductor lasers were developed. This followed a couple of years later in 1977, where there was the first demonstration of live telephone traffic through a fiber optic cable. It happened to be 6 megabits long in California. I recently had a very interesting conversation with a retiree that worked on what he called the first commercial application of fiber optics in telecommunications a few years after that first deployment demonstration. In his case, it was a fiber that carried a single DS3, which is approximately 45 megabits per second, and it could accommodate 672 simultaneous phone calls on a single fiber, which was outstanding capacity at that time. We had a very lively and interesting conversation. A fiber optic cable is a strand of glass that looks like a fishing line. When light via laser is shined in the end, the light can be transported a long distance and come out the other end. We can encode digital data, phone calls, video, and internet traffic into light, and then transmit that light to another node at the next city, or even across a country, or across an ocean, and recover that data. The process of encoding data into light is called a modulation scheme. We will talk more about modulation schemes later. With fiber, you can transmit more data for a longer distance than a wire. This leads to more traffic carried at a lower cost. In the 2000s, the telecom industry turned to dense wavelength division multiplexing, or DWDM, to dramatically increase the capacity on a fiber, thus reducing the cost per bit. If you happen to have a physics class in high school, try to remember the discussion about optical prisms. If that doesn't work, how about the album cover for Pink Floyd's 1973 album called Dark Side of the Moon, which pictures a prism on that album cover? With a prism, light like a rainbow, white light is broken down into constituent colors as depicted by Pink Floyd. With DWDM systems, light from sources such as switches or routers are converted to a specific color. Multiple colors are merged via a prism-like device into a single stream of light. At the other end, the reverse happens. The light is broken down into individual colors and sent to the specific switch or router that it was connected to. Current technologies allow for up to 128 colors to be merged. Thus, capacity of the fiber is increased by 128 times and resulting in dramatic reduction in cost per bit. The device that colorizes the light is called the transponder, and the prism system is called the line system. In recent years, there have been three prominent architectural trends in optical transport systems. They are disaggregation, open line systems, and open APIs. Each one of these architectural enhancements has led to increased capacity and lower cost per bit. I would like to just I would like to pause for the last sentence. I would like to briefly describe each of these three trends. For at least 30 years, Fujitsu and all of our competition have been developing and deploying a chassis-based system where you deploy a chassis with a slot and then with slots in it, and then add service cards to those slots as needed. These service cards have different functions, including SONET, Ethernet switching, transponders, optical blades. When it came time for Fujitsu to introduce our next platform, we could have developed another chassis and a set of cards, but we chose a different and unique architecture. We realized that as new technologies and new chips became available, the chassis constrains your design in terms of space, power, thermal dissipation, backplane speeds, etc. These constraints increased our development time and cost. The individual functions are still needed, so we chose to introduce them as a blade-based design. Quite often, a few constraints are eliminated and quite a few values are introduced with a blade-based design versus a chassis-based design. Thus, our latest optical transport system is blade-based. Many other vendors have followed our lead and adopted the blade-based products to varying degrees, and this is the concept is called disaggregation. A system is being broken down into functional elements and then developed and deployed as blades. Historically, with a chassis-based system, the service provider is locked into the entire system and is forced into using the optical line system and transponders by the vendor selected, and sometimes switching capabilities too. There has been a trend in the last few years to separate the optical line system and the transponders, allowing service providers to select the open line system they feel best and then populate that system with the best transponders available. This leads to more competition and lower prices. With the arrival of disaggregation and the open line system, the possibility emerges of having multiple management systems, which increases operational costs. Many of these products have embraced open interfaces called APIs. There are a number of sources for various open protocols, usually initiated and maintained by open organizations. These open APIs improve interoperability and provide mechanisms for orchestrators to assist in the operation of multi-vendor systems, thus lowering operational expenses. In addition to the three architectural trends, there are always technological advances that improve performance of each aspect of the transport system. Next, we will investigate some of these technological developments, starting with technologies associated with transponders. Specifically, we will describe how modulation schemes work, then look at advances in modulation schemes, new channel widths, and describe something called forward error correction, which is known as FEC. Each of these technology advances results in increased line rates or improved reach and lower cost. To start, let's go back to your high school physics class again. If you didn't take physics in high school, or like me, don't remember much from high school, don't worry, I'll make it easy. Light has dual nature. Sometimes it acts like particles. These particles are called photons, and they sometimes act like a wave. Think sound waves or a guitar string vibrating. We're going to focus on the wave aspect. There are three parameters that define a wave. As per trigonometry, it's called a sine wave. Those three parameters are called the amplitude, which is how loud the wave or how bright the light is, the frequency, which controls the color of the wave, and the phase. These four sine waves on the left side of this drawing, they all have the same amplitude, they all have the same frequency, but they each start at a different point in the cycle. Thus, they each have a different phase. That starting point in the cycle is called phase. We will start to develop the concept of using the phase to encode data into the light in the next few slides. The initial systems used for optical transport systems used a type of light called non-coherent. The phase of the non-coherent light waves was not controlled as shown in the top diagram. A wideband light signal includes multiple colors, also shown in the diagram. So these first systems had multiple colored light in them, and they didn't control the phase of the light. For a DW system, all of the colors are the same as shown in the middle diagram. You're switching a particular color, a particular wavelength. When the phases of the light waves all are the same, then you have something called coherent light. All of the phase is the same. Non-coherent light worked fine for up to about 10 gigabits per second, since we were just trying to detect if the light was on or off. So in those early systems and up until recently, they used something called on-off keying, which means you encoded into the light whether the light was on or off, kind of like Morse code. And that's how you encoded data in and recovered it at the other side. But at higher rates, we were not able to detect whether or not that light was on or off properly. So we were unable to use the on-off keying and the non-coherent light to push to a faster and faster data rates. But we were able to control and detect the phase of coherent light at higher rates. That's how we moved to 100 gig and beyond 100 gig by switching to coherent lasers and encoding the digital data into the phase of the light. With data rates of 10 gig or less, as I stated earlier, we used on-off keying, which is like Morse code to encode the data in the light. But as we moved up to 100 gig, that didn't work. So we can use the phase of the coherent light to encode data into the light and recover that phase and thus recover that data at the other end. This encoding of data into light is called the modulation scheme. The most common modulation scheme for 100 gig is called QPSK, which is quadrature phase shift keying. With QPSK, we used constant amplitude and a single color and 4 different phases, hence the quadrature. The quad means it's a 4 phase shifts. Specifically, as on the little drawing on the right, if you draw those quadrants, we will be using a phase of 45 degrees, 135 degrees, 225 degrees, and 315 degrees. So during each period, we are sending one of these 4 dots on the right side of the screen. If that dot is in quadrant 1, we have sent 2 bits, 0, 0. If the dot is in quadrant 2, then we send 1, 0. If the dot is in quadrant 3, a 0, 1, or if it's in quadrant 4, a 1, 1, or some variation of those combinations. But the point is that you are sending 4 different phases, and those phases are imply 2 different bits. This is shown on the bottom right diagram of the sine wave, where the amplitude and the phase, the frequency of the sine waves is the same in all cases, but during each time period, the phase shift. Again, we can control that phase at this high rate during each time period, and we can actually recover that at the other end of the light scheme, at the other end of the fiber, and that represents 2 bits of data during each time period, which of those 4 phases was being sent. Now, there are many different kinds of modulation schemes that use phase. Here are some of the more common ones in modern optical transport systems. The first one is QPSK. That's the one we talked about on the previous slide, and it uses 4 phases. The second one shows 8 phases, which results in sending 3 bits during the time period, and it's called 8 PSK. To send even more data, we will use the amplitude and phase to encode data into that light, and it's called quadrature amplitude modulation. So quadrature for using phase and amplitude in the modulation. And the third one is something called 16 QAM. There's 16 points, which is 4 bits of data modulating into amplitude and phase. Each during the time period, you'll get one of these 16 points is what will come across, and you can detect which one of those is and determine which of those 4 bits were sent. And even more bits per time period, you can use the 64 QAM to get even more across there. So that results in more data on the optical link and thus reducing price, reducing the cost. But there's an interesting phenomenon. As the number of points in this constellation goes up, the distance you can reach, or the distance you can go, goes down. So I will explain that in the next 3 slides. Why is that? Light being sent down a fiber is a lot like looking through a window. If something is very close, it's very crisp. As the objects you are looking at get further away, they become fuzzier and hard to distinguish. That's because there are optical impairments that impact the crispness of what we see. There is heat, there's rain in the air, moisture in the air, there's distortions in the window, there's dust in the air, there are birds flying, there's trees and leaves. All of these things contribute to a limitation of how far we can see through that window. While on the optical fiber, there are also a number of impairments, actually quite a few, that get worse with distance, just like when you look out the window. As this slide shows, as the distance increases, the dots get more fuzzy, and the size of that fuzziness gets larger with distance. At some distance, some faraway distance, the fuzzy dots overlap, and we can't tell which one it was supposed to be. So at a long distance, we may think the dot is in quadrant 2 when it's actually sent was in quadrant 1. When this happens, we take errors as we convert it back to the wrong set of ones and zeros than what was actually sent because of that noisy environment, because of those impairments. And in this case, that message, call, or video during that time period has been corrupted because what you think it was is not what it was actually is, so it takes an error. With higher modulation rates, the dots are closer together. Consider this illustration. Notice that the 4 dots associated with QPSK on the right and the 64 QAM on the left there, they're closer together when they're 64 QAM. Thus, as you get more and more distance, the dots grow, you can handle less distance. Let's start over with this one altogether. With higher modulation rates, the dots are closer together. Consider this illustration. Notice that the 4 dots associated with QPSK on the left are much further apart than the dots associated with the 64 QAM on the right. The 64 QAM can tolerate less fussiness or distance than the QPSK before we start to misinterpret what is received and takes errors. That's why more complicated modulation rates have less reach. It gets even worse when we get up that 64 QAM. Those dots are much closer together, can accommodate much less fuzz. These are actually shots. Let me start over on that one. These are actual screenshots of the eye diagrams of the constellations for these three modulation types from three of our one-finity transponders. Wow. How do you actually differentiate? Start over again. These are actually, start over again. These are actual shots of the eye diagrams of the constellations of these three modulation types from three of our one-finity transponders. But that looks pretty amazing on the right one. How do you actually differentiate the points for that 64 QAM constellation? In order to do that, it requires another technology called forward error correction. Forward error correction is a mathematical technique to detect and correct a limited number of errors in the transmitted data without the need for retransmission. This method, the sender sends a redundant error correcting code along with the data in that frame. Using that redundant code, you can correct an error-prone block of data. So earlier I said we weren't going to do any math, which is true, but we will describe what math is doing and what its benefits are. Here's an example here. Here's a simple and inefficient FEC algorithm, forward error correction, that no one would use, but it is illustrative. Consider that you want to send a 0 or a 1 over the fiber. In this algorithm, if you want to send a 0, you actually send 3 consecutive zeros. Similarly, if you are sending a 1, you actually send 3 consecutive 1s. That's why this algorithm is not very useful. There's 2/3 overhead, 2 extra bits of overhead for every bit of payload. Not very efficient. Now, what happens on the receive side? If we receive a 000, a 001, a 010, or a 100, then you declare that a 0 was sent. Similarly, if a 111, a 110, a 101, or a 011 is received, then it's presumed that a single 1 was sent. And that way, if there was no error in transmission, or if their single bit was error, that means that bit gets flipped. There was a little bit of distortion out there, and we thought we received the wrong bit. We will convert it as the wrong bit. Then the correct transmission can also be received because of that overhead. Even if any one of these ones shown here or zeros that has been flipped, we still know what the original data was. But this comes at the expense of that overhead, in this case, 2 bits for every 1. With forward error correction like this, you can send data further and still recover the original data with confidence. This is not only used in optical transmission, but also in wireless transmission. Your cell phone could not function properly without these types of error codes. The first forward error correction came out in 1947 by a man named Hamming. Later in 1960, a collaboration between Reed and Solomon developed a better code now known as RS-FEC, which is still in use today. And then there's some other developments from more developments across time, EFEC and UFEC. And at this point in time, virtually every vendor has their own proprietary soft decision FEC. And the whole idea here is to do this correction with lower and lower amounts of overhead. Previously, I referred to the light as having a color, but I need to point out that the DWDM multiplexer doesn't combine single wavelengths. It actually combines a band of wavelengths. So it's not green, red, and blue, but a group of greens and a group of reds whose wavelengths are all within that band. Soon after these DWDM systems were commercialized, it was agreed through some standard that the band would be 50 gigahertz wide for each color, and these bands were standardized as shown in the diagram on the left here. There is also a set of equipment that uses wider bands of color called coarse wavelength division multiplexing, or CWDM. This standardization alleviated the possibility of each vendor using differently defined bands that would make interop almost impossible. This arrangement worked very well for the entire industry for the last 20 years. But as we move to these more complex modulation schemes, in order to achieve a similar distance, the band may need to be greater than 50 gigahertz. You can't put a larger band, say a 75 gigahertz band, through a 50 gigahertz grid. Part of the signal gets chopped off, which is shown in the bottom left corner here. The idea of using a larger fixed grid, such as 100 megabits or 150 megahertz, the idea of using a larger fixed grid, such as 100 megabit hertz, one more time. The idea of using a larger fixed grid, such as 100 megahertz or 150 megahertz bands, is a viable strategy and works with some applications. This is shown in the middle drawing here. But in environments where you have mixed bandwidths, that spectrum is wasted, as you can see in this middle diagram. If you have a 50 gigahertz channel, you're wasting spectrum, and that's very expensive. As these other modulation schemes have become more prevalent, accommodating a variety of bandwidths instead of a fixed grid is desirable. The vendors have met this need with a concept called flex grid, where a variety of bandwidths can be accommodated, thus continuing to efficiently use the entirety of the spectrum as shown in the right diagram. So if someone ever mentions the term flex grid, this is what they're talking about. The heart of the optical transport system is a reconfigurable optical add-drop multiplexer, or ROADM, R-O-A-D-M. As described in the acronym, the ROADM will add and drop some number of individual wavelengths or colors, or actually color bands, to the fiber that carries the multiplex signal to the next optical node. The multiplexed fiber is called the line side, and the individual signals being added are called client signals. The conversion from a colorless wideband signal to a colored narrowband signal is accomplished with the transponder, and the ROADM has a few transponders are being depicted in this drawing on the right here. The ROADM itself is comprised of a device that actually adds and drops and passes individual channels within that optical light, within that fiber. And the drop complex is what is usually described as, let me start over again, I'm sorry. The ROADM itself is comprised of the device that actually adds, drops, and passes individual channels within the fiber. And the drop complex, and I have my text wrong. I'm going to have to wing this one here. Start over again. The ROADM itself is comprised of a device, usually called a wavelength selector switch, or a WSS, that actually adds and drops and passes individual channels out of that fiber. The WSS is a component that switches these channels, pulls the ones out that need to be dropped, or passes the one that need to be dropped. The second part of the ROADM is the drop complex. The drop complex brings the individual channels to the WSS. There are a variety of drop complex technologies. Some of the more common complexes that you may hear about are listed right here: colorless, directionless, colorless and directionless, and CDC. We will describe each one of these drop complexes and identify the value of each one in subsequent slides. As mentioned in the previous slide, ROADMs can have a number of degrees as shown in the diagrams in this slide. A ROADM can have 2 degrees with an eastbound and a westbound fiber with all of the channels on it. A 2-degree ROADMs are commonly used in linear deployments or ring deployments. A 3-degree ROADM has a third spur going to a third path. 4-degree ROADMs are commonly used to connect 2 rings together, or just 4 fibers that are coming together at a site. Higher degrees are also used, although somewhat rare. In Fujitsu's long history with ROADM systems, we have found that approximately 70% of the nodes deployed are 2 degrees. 3 and 4 degree ROADMs are the most common ROADMs that are greater than 2 degrees, and up to even 8 or 12 degrees are used in some rare instances in some large optical networks. So that's what's being referred to when someone says how many degrees a ROADM has, how many of those fibers are coming out. When DWDM was first deployed, a fixed multiplexer was used for each of the degrees as shown in this diagram. An arrayed waveguide, or an AWG, is the most common way to provide this capability. This is a very rigid drop complex. You need to get the client signal being added or dropped connected to the specific AWG associated with the specific degree. Additionally, you need to get the fiber connected to the specific channel number on the AWG that matches the color that you've tuned that fiber to. If you change colors or channels or change degrees, the fiber must be disconnected and reconnected to the specific port on the appropriate AWG, which is a very labor-intensive process and subject to human error. But it is a cheap and easy drop complex. The next development in drop complexes was the replacement of the AWGs with a device called a splitter coupler. Splitter coupler simply takes some number of channels and couples them together, or splits them apart if you're going the other direction. With an AWG, each port is specific for a channel, whereas with a splitter coupler, the ports are all independent. All of the ports can be simply colored to whatever you want and then sent to the WSS. So you don't have to, you have to get it to the right splitter or coupler, but you don't have to get it to the right channel. It simply combines all the colors and sends them to that particular degree. There is still a splitter coupler per degree or direction, but the channels can be connected on any port in the splitter coupler, thus simplifying automation and eliminating a source of miscabling. Next came a technology to eliminate the splitter coupler per degree, and it is a 4-port splitter coupler. So the splitter coupler can then be used to send a specific channel to any of the 4 degrees. This type of drop complex is called colorless and directionless, since it can go any direction, or a CD drop complex. This advancement further improved automation. Just plug the channel into any port and it can be routed to whichever degree is needed. This makes a fiber cut much easier to route around. If the fiber is cut, each of the channels can be remotely rerouted to one of those other degrees. Thus again, improving automation and reducing error. There is a restriction in a colorless, directionless, or CD drop complex. The restriction is that all of the client ports on that splitter coupler must be unique colors or channels. You are restricted from sending 2 different services that use the same color or channel through the same CD splitter coupler to 2 different degrees. This is called contention. Because it is a coupler, all of the channels are simply added together. They're coupled to that output port. And if you're using the same color or channel twice, they obliterate each other. You can't tell any of them apart. If you have 2 routers, or even one router that has a connection that goes east and a connection that goes west, you cannot use the same color going east and west because of this contention on the splitter coupler. There is an easy way to work around this contention. Simply use 2 CD splitter couplers so that each color can be unique. Although it was slightly more costly to deploy 2 of them, it does allow you to use the same color in multiple directions and thus eliminating contention. The most elaborate drop complex adds a WSS in the drop complex, shown on the bottom there. The drop complex has a WSS in it, and that allows you to deal with this contention also. So it's called a CDC drop complex, colorless, directionless, and contentionless drop complex. The CD drop complex further enhances the automation and reduces most all of the manual operations. With a CD drop, simply connect the channel to the CD drop, regardless of the color or direction. It can be remotely routed to the correct degree, and it adds cost since that WSS is relatively costly, but it reduces even further the amount of errors that are likely prone to be having errors, and makes more automation. It is permitted in a design that has multiple ROADMs to mix and match CD and CDC complexes in a single optical transport network. A CD drop complex makes a lot of sense at very large degree nodes with lots of drops, whereas a CD drop complex makes more sense at 2-degree sites where the likelihood of contention is far less. This slide presents a side-by-side comparison of CD and contention and a CDC drop complex. So if you want to see all 4 of those previous slides put together, review this slide sometime. With these technologies and building block approach, the number of unique networks that can be constructed is limitless. Additionally, you can deploy the initial network with just the functionality needed and then easily add to the network as growth occurs. So you have a minimal entry cost with unlimited growth. As I started this presentation, I think it is evident that there's a lot of physics, technology, and terminology associated with optical transport networks. Hopefully, we have removed some of the intimidating aspects of this terminology and that these concepts are more easily understood. Hopefully, you will feel much more confident and conversant in these conversations. Thank you for your time and have a great day.